Okay, let's have some fun with Kirchhoff rules. We'll see if we can't figure out how these work. Well, it had to happen sometime. I'm honestly considering during your next exam just putting on that 10-hour loop of Lizard and just letting it run. No, it does, but it doesn't bother me. All right, Kirchhoff's rules. So here's the way I did it. I went around the top loop that way, the bottom loop that way. Let me get my little microphone out. Make sure people can hear. All right, so we said that I3 is I1 plus I2. Again, when you're looking at these, you have to really try to pick which currents separate and where do they come back together to figure out which current equals the other two. Okay, so for my bottom loop, I'm going to have, and remember I called this battery 1 and that one battery 2. You don't have to call them, you don't have to do it in that order. It's just how I did it so you can make sense of what I'm doing. Delta V of battery 1 plus delta V is 6.0. Delta V of 2.0, everything has to equal 0. So the way this is going to look, see if this makes sense to you. 10 volts, 6.0 I1 minus 2.0 I3. So the positive 10, we go from negative to positive on the battery. That's going to be a positive EMF. Oh, I forgot to put the voltages on here when I made this. So this one, that one's 10 volts. That one's 14 volts. Okay, so then I go across the 6.0, the 6 ohm resistor in the direction of I1. So that's going to be a negative IR. And then as I go around I3, I go across the 2 ohm resistor in the same direction that I3 flows. And that's going to give me a negative IR. Can you make sense of why going in the direction of current gives you a negative delta V? Electrons go the opposite way. Okay, so much space to I should have plenty of space. Okay, so top loop. So I just started with the the 4 ohm resistor. So delta V of the 4 ohms, delta V of battery 2, delta V of the 6 ohm resistor, delta V battery 1 equals 0. And if we go around that loop, what we end up with is negative 4 I2 minus 14 volts. Again, that one, because we're going from positive to negative, is going to make the EMF negative. Plus 6 I1. minus 10 volts equals 0. Now I have three equations that I can end up solving. So this bottom loop, I ended up solving for oh, hang on. Gotta do a substitution first. Okay. So I'm gonna do 6.0 I1 minus 2.0 I1 plus I2 equals 10. Oh, sorry, plus. Because I moved the 2 and the 6 to the other side. And I end up with 8 I1 plus 2 I2 equals 10. I can work with that. How can I simplify this second one? Well, so, let's see here. Well, so what did I do if I do this? So I'm gonna move the voltages to the other side of the equation, and then I'm gonna do something. You know, I don't need the volts, but it was 5.0. What'd I do? Yeah, I divided everything by 2. And so then I'm just gonna set it in the order of 3.0 I1 minus 2.0 I2 is gonna equal 12. Now I did this for a reason. What can I do next? How can I get rid of either I1 or I2? Yeah, if I add the two equations together, 2I2 and minus 2I2 will cancel out. Okay. Well, let me grab this one first. Okay, so 8.0 I1, 2.0 I2 equals 10. 3.0 I1 minus 2 I2 equals 12. Yep, this will give me 11. I1 equals 22. I1 is 2 amps. Yep, there's one of them. So where did you end up using the quadratic formula? Then why did you ask? So the question was, would using this thing that I actually didn't use be appropriate? Oh, okay. So now let's take this first equation. 8.0, so I1 becomes 2. Plug in that. Now it's going to give me 16 plus 2. You get a negative 3 amps. Now, remember, I3 is I1 plus I2. I3 is then going to be a -1 amp. Okay. Which one of these currents will kill you? All of them. The beginning of the lethal range is 0.5 milliamps. These right here wouldn't just kill you. These would, well, not, probably not, but I always say make your heart explode, but I don't know if that's actually a thing. I think that the amount of clearance we would have to get to experiment with that would be ridiculous. Consent to be killed in an experiment. I don't think you're going to get that. So that's Kirchhoff's rules. Now, some students latch on to Kirchhoff's rules for a way of solving circuits. Some latch on to the more traditional way of finding like equivalent capacitance, equivalent resistance, and going that route. Series and parallel circuits. So electric devices wired to the same, so that the same current flows through each one are considered to be in series. Okay. Now your equivalent resistance. Now, okay, I want you to pay attention to something. You're going to notice that your capacitance and resistance are like opposite formats. So if you can remember one of them, you have the other one. So for example, in series, your equivalent resistance is just adding all the resistances together. From the lab, what was capacitance? 1 over CEQ is adding 1 over all the capacitance. Okay. So here we see 2 resistors in series. They both have the same current running through them. So let's just say for fun, I'm going to go around the circuit that way. So if I say, well, what is my sum of voltages? Where I get the voltage of my battery. In this case, actually use that for something. Okay. 1.5 volts. I don't think we need that, but whatever. So then I'm going to have delta V of R1, delta V of R2 equals 0. So this is going to be 1.5 volts. IR minus IR1 minus IR2 equals 0. So I'm going to get IR1 plus IR2 equals 1.5 volts. So then I can factor out the I. And we notice that 1.5 volts is the entire voltage of the system. So that means that this one current multiplied by some pretty much total resistance of the circuit, or equals the total voltage put out by the battery, which is where we end up getting okay. So here's some fun things. EMFs in series. So this is kind of a nice mock-up. You can see the batteries with their voltages, so their electromotive forces and their internal resistances. you can see a load resistor. Which one's the load resistor? R. Why is it the load resistor? Yeah, it's outside the power source. So remember your circuitry outside the power source that needs to be run by a power source is called the load. So like when you're watching Iron Man, he said this feeds into the load circuit. Well, he's talking about the circuitry that runs the rest of the suit. Okay, so you have some basic equations here. So you see that you can do an equivalent EMF and an equivalent internal resistance in the same manner that we just did REQ. Yep, the little r is going to be your internal resistance to the battery. That does not narrow it down. Oh, oh yeah, the little dotted. So that's what these are. They just drew it to look like actual batteries this time. Does it? Okay. Yeah, the little dotted box is supposed to represent a whole battery. By the way, this morning I was thinking about just getting you know how coffee pots have that little hole on the top? I'm thinking about getting a straw.
Yeah.
Just take it off just take it, put the straw in it, just sit it down at my desk. It does. But then I wouldn't get to use my jack-o'-lantern mugs. Because there are two seasons in every year. There's Halloween and then there's December. No. No, don't bring up Christmas. Sometimes you are so happy and sparkly. I can't. Okay, so now one thing that we'll be able to see is that for an entire circuit, how to label this. I'm just going to call it total R. So for this circuit here, we can actually go load resistor, this R1, R2, R3, R4. We can actually include the internal resistances in the total equivalent resistance of the circuit. So, of course, these are our currents. So let's follow our current around. Well, let's see. So we have E1, E2, E3, E4, It does show you that you can do a circuit of just about any size with Kirchhoff's rules. You're just going to keep adding the delta V's as you run through your path. So what this will give us, based off the way that the circuit's going, so current's going that way, goes up and around. All of our delta V's for the electromotive forces And then we're going to have minus IR. So what we can say then is now we'll pull out current. So we can get a an equation for the current of our system. So we can't actually use, so this is one way you can solve for current. You don't necessarily have to use this when problem solving, but it is a way to do it. So you're going to notice with circuits, there's a lot of different ways that you can solve the problems. There are some, you can figure things out by looking at your Kirchhoff rules. You can also remember certain theorems, if that's what you want to do. So what would this, huh? You could, well, what, so skip to at least this version to show that you know what it means. It's more fun to do it the long way. Actually, that's easier for me to do. Me trying to suss out your shortcuts makes the grading take longer. And I'm usually annoyed by like the fifth assignment. So try to get yours on the top. So I usually look through and I go, I like that person. And I start putting those on the top so that then I get those done before I'm just like, nah, I'm really annoyed. I put his above yours. Hey, well, what's the phrase? Play these games, get these prizes. Now, you'll notice we've come to capacitors in series. So you see how now we have the 1 over the CEQ is going to be the sum of 1 over all of the capacitances. Okay, so where this really comes from is what was one of our first equations for current? No, think of it in terms of a change, changing something over change in time. Kind of. Hmm? Yep. This is our delta Q over delta T. Now, since they're in series, each capacitor has the same charge. Now that'll change when they're in parallel, but this is one of the keys to remembering how to solve when you're analyzing circuits this way. In series, they all have the same charge, just like they have the exact same current running through them. So they're all going to have the same charge. All righty, well, we're going to go that way around the circuit. And a lot of the theorems you see in the textbook can be derived by simply using Kirchhoff. So you could also just use Kirchhoff to solve your circuits. However, there will be homework problems where I tell you to solve it, which way to solve it. So, because I want to see you can do both. Now, when I put these delta V's in for my capacitance, so I'm going in the direction of the current, going from positive to negative across the capacitor. What will the sign on that be? What happens if I go positive to negative across the EMF? It becomes negative. What if I go positive to negative across the capacitor? Because it becomes negative. So I'm going to have my electromotive force. My electromotive force can be voltage for C1, voltage for C2, and then what am I going to plug in for, well, let's see. So what do we know? What do we know delta V of a capacitor? If I start from delta Q over T for current, work my way through, what do I get? Okay, what is Q equal? Someone said this earlier. So with capacitance, Q equals what? C delta V. So what's delta V going to equal? Okay. Now they each have the same Q, so eventually that's going to pull out of everything. But let's kind of take a look now. What we're working towards when we do an equivalent, either resistance or capacitance, it's like taking all of the capacitors or resistors in the circuit and turning them to one single capacitor or one single resistor. So you can always redraw the diagram with just the one. All right, so in this case, we could do Kirchhoff again. And now I have this expression and this expression, so I can say Q over CEQ equals Q over C1 over C2. And what can I do with the Q's? What can I do with those now? Divide them out. And so, of course, you could just keep going and going and going with it for as however many capacitors you have. Yes, because you will have more homework assignments where you have to do some deriving. I want to make sure you can understand logical arguments. Plug and play is okay for freshman year. It is not okay for juniors. Yep, not okay for juniors. Yet you're in here with all of them, so you're in here with all of them, so you have accepted that upon yourself. That is a choice you made. Yeah. Well, kind of like if you ever get pulled over by the police and you're like, yeah, but that wasn't me. They're like, well, but you chose to be here. Well, the police here in town don't have a lot of crime going on, so they. No, sometimes they do, but don't do it near the high school. So let's see, yeah, so let's see if we can find the CEQ of this system. Let's see, our voltage. So our electromotive force is 18 volts. Okay. Now, I'm going to do this by keeping everything in microfarads. You can do that as long as you know what units you're in and what compares to what. So eventually, when I get to delta V times CEQ, I can't multiply volts by microfarads. I have to multiply SI by SI. So in that case, it'd have to be volts times farads. Well, I mean, I could. I guess you just have to remember. Would you be, okay. Would you be able to tell me what unit you ended up in if I multiplied volts by microfarads? Delta V times C gives me what? So, right. So see, delta V times C is Q. So this is why I always change things to SI unless you know exactly what units you're going to be getting, because your volts times microfarads would give you microcoulombs. But if you don't get that, just translate everything into volts, coulombs, farads. Don't start messing around with SI units until you know, make sure you know exactly what you're doing. Now, in the case where they're all micro, you can leave it that way and your answer will come out as micro. This first one is let's see, this is going to be 1 over 3 microfarads. Use your calculators and tell me if you get this. And then tell me why that's my unit. Yeah, because the microfarads are in the denominator. Oh, again, remember, negative exponents means it goes in the denominator of a fraction. Now, granted, I could say, let's say I pulled a Tim Keith and told you no calculators. You could change all these denominators to 24 and then add everything up. So the first one would be 8/24. The second would be 6/24, 2/24 plus 1/24. Did we get this when we put it in our calculator? Well, that wasn't a very good idea, was it? Yeah, you can do that. Make sure you're using parentheses to save your life.
Yeah. I guess it's the same.
Okay, good. So now how do I get the equivalent capacitance? How do I get the equivalent capacitance?
One over that.
Yep. That's horrible. Is everyone still familiar with that step where I have to invert it? Okay, what about the voltage? Let's see, what's the next part? The voltage for the capacitors, each capacitor. Now, here's a question. They all have the same charge, but do they all have the same voltage? Right. So the first thing we want is the total charge of the system. So that's going to give us the charge on each capacitor. And so we can find that. You can always use the equivalent to find a total number. What would this be in microcoulombs? Not 0.28. 28.8. Because micro has to be 10 to the negative 6. So I just move the decimal one to the right. Now that I have the charge that's going to be on each capacitor, how do I find the voltage on the 3 microfarad capacitor? Yeah, you do. So what we're going to have is Q. So I'm going to use micro for each of these, and I want to see if you would have gotten this. Microcoulombs divided by microfarads gives me 9.6. What's the unit? Nope. It's a delta V. Yeah. So you notice how that doesn't give me microvolts. Yeah. So if that confuses you, just go ahead and change those both to times 10 to the negative 6 coulombs per farad. And so then we just do this for all of them. From what I'm hearing, you're prepared for a Keith type exam, no calculator.
Well, you reduce it. You reduce it.
Mhm. Very true. But again, what I'm hearing is you are ready for an exam with no calculators.
No, 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 no. No, no, we're not. We're not. No, I kind of understand.
Okay, so that's capacitors in series. So what we're doing now, this is another way, like outside of Kirchhoff's rules, that you can start to solve these systems. You can have systems of parallel series. You can reduce them all down to your equivalents. You can find out like either total voltage or total charge, and then start breaking them back apart. So here's resistors in series. We'll get this one started. So we have 6 volts for our EMF. So A, find the equivalent resistance in the circuit. So that one's pretty easy to do. We like resistors in series. We're also going to like capacitors in parallel. Because you notice how capacitors this time are 1 over C and resistors are just adding the R's. When you go to parallel, you just add the C's and it's 1 over R. So they're the exact reverse of each other. So part B, the current in the circuit, if the terminal voltage of the battery is 6 volts. If you saw that terminal voltage of the battery, how would you interpret that? You know, I think I'd prefer you just say 6, 7. I really, I think I know, I know. I think I'd prefer 6, 7. So the terminal is the total voltage the battery puts out. So when it says that, we're not worried about EMF versus internal resistance. We're not worried about that. It's just, this is the voltage of the battery. Yep. So you just say my battery's 6 volts. That's what it's putting out. And what is a good equation relating delta V current and resistance? When I do my Kirchhoff's rules, what do I put in for the delta V of a resistor? Yeah, V equals IR. So then I can say current is going to be delta V, and I want the current of the whole system. Well, it's going to be this. So I just want the current of the equivalent resistance. Okay, we'll continue with this on Monday. So, and as we go along, try to pick a way that you like to solve circuits. Well, you like resistors in series. You'll like capacitors in parallel better.